Today we shall be looking at a form of the Schrodinger equation that you have never seen before. The general form of the Schrodinger equation that you are familiar with is this, where U represents potential energy. My aim is to prove that the term U psi can be written as a first-order derivative of psi. So let's dive into it. The different types of potentials are the gravitational potential Gmm on R, the electric potential kQq over R, where K here represents the Coulomb's constant, and the elastic potential 1/2 kx squared. The goal is to show that all these potentials are linear in terms of the wave number k. For a particle or object moving in a wave-like manner, the distance x covered in any given time is a multiple of the wavelength. That is, x is equal to n lambda, where n is a positive real number. The simplest example is a particle moving around a circular path. For one cycle completed by the particle, n is equal to 1, and by definition, the distance covered by one cycle of a wave is called the wavelength. So, x equal to lambda, which is equal to the circumference of the circle, 2 pi r. Now that we have validated this equation, x equal to n lambda, let's invoke this other equation from the wave theory. Subbing in this expression for lambda yields x equal to 2 pi n over the wave number k. The case of gravitational potential. The expression for gravitational potential is as follows. Multiplying and dividing by 2 pi n yields this. Look at the denominator. 2 pi r is the circumference of the circle, which is equal to lambda, and lambda times n is equal to x. So our potential becomes 2 pi n gmm over x. Also, x is equal to 2 pi n over k. So subbing this yields u equal to gmm times k. We can also write it as u equal to b1 times k, where b1 is equal to gmm. The electric potential. Electric potential is equal to this, where k is the Coulomb's constant. By the same argument, we can show that u is equal to kqq times little k, which can also be written as b2 times k, where b2 is equal to kqq. For the case of the elastic potential, we know that elastic potential U is equal to 1/2 kx squared. This can also be rearranged as follows, so that we can write U equal to B3 times K, where B3 is equal to 1/2 x squared. So in general, we can write potential U equal to B times K. Multiplying both sides by the wave function psi yields this. For this form of the wave function, the psi dx is equal to ik psi. So k psi is equal to minus I d psi dx. Therefore, u psi is equal to minus b d psi dx. The term minus ib is just a complex number, so we can just write b to represent it. Therefore, our Schrodinger equation becomes a d square psi dx squared plus b d psi dx equal to c d psi dt. For the general wave function psi equal to e to the power I times kx minus omega t, to be a solution of the Schrodinger equation, a must be equal to minus h bar squared over 2m. C must be equal to IH bar, and B will depend on the type of potential considered. You might be surprised to know that taking away the complex number I from the wave function will not affect the form of the Schrodinger equation or any other quantum mechanical equation such as the Dirac equation, the Heisenberg uncertainty relation, the difference commutation relations, and so on. Click on that subscribe button and join me in the next video to see how this is done. What you will discover is that it is not the math of quantum mechanics that is wrong, but rather the interpretations that were forcefully adopted because of the presence of the complex number I in the wave function. Please endeavor to like and share the video to promote this channel. Thanks for watching.